Real quick, I'm going to do problem 3.1. This is with that beam sag or the wire sag thing that a lot of people had issues with. You have to excuse me while I'm eating dinner while I'm doing this, so there might be some awkward pauses. So we have this wire on two rigid supports, and there's a bunch of 300-pound weights hanging off of it. We want to know what this sag is, HC. We know that this is 4 feet, right there, and that is 10 feet. So, the first question, and what we want to know is what's the tension in the end here? There's got to be some support load like this, and obviously some support load like that. Let's call it tension in the Y direction, we'll call it tension in the X direction. Not really tension so much as, we'll call it the support at what? E, EY, and EX. So EY is probably the easiest one to figure out. You can actually just immediately look at this, note that it's symmetric, ergo, you can just take the whole amount of forces and divide by 2. It has to hold up 900 pounds total, so this would be 450 pounds. That's the easiest thing. And then we have to find EX. This is a little harder because there's a sloped wire here, but we know that the total of EY and EX is some little vector here that is in line with this wire. So if you have a wire, the tension must be exactly along the wire. We know that for every 4 up and 10 over, it's the way the wire points. Likewise with a force. So this equals 450 pounds times 10 over 4. And that's how we use our little proportional trick here to get, I just know by memory, 1125 pounds. Make sure that that's correct. Okay, now let's look at D. Point D. We have the weight of 450 pounds, or 300 pounds. We have EY, and we know what the tension of this wire is, so there's a upload of 450 pounds from the wire. There's a tension this way of 1125 pounds. And we want to know basically what the tension is in the wire on the far side of this to make all these known things 0. There's nothing else in the horizontal direction, so the horizontal tension remains unchanged because there's no horizontal load. 1125 pounds. And now we know that the vertical force has to be reduced by 150 pounds, which is the difference between these. The wire has to change slightly so that it's pulling with 150 pounds additionally down. So this is a little crowded. So if you look at D, we know that the wire on the left of D is pulling this way. It's 1125 pounds. And is pulling this way with 150 pounds. So intuition check, does this make sense? The answer is absolutely, because if you note that the vertical force in the wire is 150, if you look right here, that has to be the case. There's a 300-pound load in the middle. By symmetry, the load here and the load here has to have a vertical component of 150 pounds by symmetry. So now we know this is what the angle that the wire goes on. And we know that geometrically the wire follows the same proportions. So over 10 feet, it goes down some distance in this proportion. So to figure that out, we do 10 times 150 over 125 pounds, which equals 1.333 repeating feet. So that means that in the little section right here, it goes 10 feet over and then down 1.33 repeating feet. So we know that this was 4. To find HC, we do 4 plus 1.333, so on. We get 5.333 feet. Now there's actually another way you can solve this if you're clever. If you look at the right section of the wire right here, here, let me do this. If you look at that right section of wire, this is in static equilibrium. All the forces and moments on this business have to sum to 0. There's a 300-pound load here. And let's say we cut this wire mathematically just to the left of this load, like so. So there's a 300-pound force there. We know that the horizontal load here at the support is 1125. The vertical is 450. And we know that the horizontal tension of the rope doesn't change. There's also a horizontal load here of 1125. Now, if you draw basically the lines of actions of all these forces, you'll get a bunch of lines that are already there. And let's see. If you look at where a bunch of them cross, those are usually a good place to try and use a moment calculation. Let's try right here at a point we will call, it's tempting to call it C, but that's this point. It's not C. We'll call it F. The moments about F, even though it's not on the wire, the moments about any point on this wire have to sum to 0. So note that the moments about F sum to 0. So what does that lead to? We have 450 pounds times 20. Rotating this way, so it's positive. This force, line of action, passes through F, so it's 0. This force, 300, has a 10-foot moment arm. If you look at basically the line of action is here. Perpendicular distance is this, which we know is 10 feet. So we do minus 300 pounds times 10 feet. And then this 300-pound force, line of action again, goes through F, so it's going to be 0. And then we have this force, which has a moment arm of HC that we don't know. So we know that that causes it to rotate negative, so minus 125 times HC equals 0. Now, we solve this. See, we have 125 HC equals 450 times 20 minus 300 times 10. So we have HC equals, this business on the right is 6,000 over 1125. Lo and behold, same answer, 5.33 feet. It's actually pretty beautiful when you think about it, that all the equations that we do are all perfectly self-consistent in the real world and in math. So you can solve this any number of ways you can think of. You can take the moments about some really unpleasant point out here. You will eventually still get the same answer.